Hello and welcome to coding demos for the Atari 2600 video computer system. So as LFT before me, I want to also start by asking some questions. Who has seen the talk that I gave at the Chaos Communication Congress? Then I did it right, okay. You know about some parts of this already. And who has done 6502 coding? So, okay, this is the audience. So, let's just have a small personal background concerning the Atari. I got my first one as a kid for Christmas. Sold it 2 years later to buy a Commodore 64, where I started coding, also some years later in assembly language. And then in the early 90s, there was this very cheap bargain to buy a 2600 back again. So that lay in the drawer somewhere back then. Then I started as a birthday present for a friend of mine, porting the 2600 emulator to the Sega Dreamcast. And today I spend most of my time coding in C++ and Qt projects. So why am I doing this talk? Why am I giving this talk? It was intended as an addendum to the Ultimate Atari talk, but it's also focused to stand on its own so that you can use this talk to get into demo coding. It is, as far as I could tell from doing some research on the internet, it is the most retro hardware you can get without spending big money or hacking, doing some serious hardware hacking. Spending big money to go more retro, that would be the Apple I computer. And hardware hacking would be the Fairchild. But, okay, even though the hardware is very ancient, it's more than 35 years old by now, there's still much to discover. Since the revision 2.0 last year, only 10 prods were released. And 6 of them were done by only one guy. So he needs competition. And still, it's the most fucked up hardware I've encountered so far. I couldn't have this. There are a lot of information that I found on the internet assembling this talk. Special big thanks to the guys at Atari Age, who are a very friendly community, mostly game coders, but they will also help any demo coders and support them. So what do you need to start? First of all, you don't need hardware to start. You can write your code and run it inside an emulator. All necessary code, the assembler, the emulator, are available as source code, so they are platform independent. You can port them on whatever you use. So far, I've met Windows users, macOS users, and Linux users. What you need for a software? You need an emulator. This will be probably Stella. It's the most mature, best maintained. Also, the code is also being grown a bit old, so it's not easy to maintain. It has the very cool feature, it has an integrated debugger, which we will take a look at the end of the talk. We have several other features. That has several other features of analyzing the behavior of the hardware inside the debugger. And the emulation is very good, but it's not perfect. One of the common problems you will run into is you code something, it runs in Stella just beautifully, and then you will notice you're doing something that won't work on the real hardware. For coding, you need an assembler. Basically, there are two choices that I've encountered. DASM is the de facto standard of the 2600 scene, and I'm using S65 of the CC65 package because I've encountered it before on hacking Commodore projects. And they have both advantages and disadvantages. If you don't have a reason to pick the S65, I suggest you go for DASM because there's so much template code available already. And You can also, it's really easy to take then over code for others, work with others together, because about 90%, 95% are using DASM. And for rapid development, there's also Batari Basic, which is a basic dialect, and it has a very fine integration with assembly language. So there's a very good options to mix assembly language and that Batari Basic. But I have, this is just what I've read about the Batari Basic on the Atari Age forum, and I haven't encountered any Batari Basic code myself. If you want to go for hardware, you need a module you can upload your code to. There, the de facto standard is the Harmony cartridge. It's capable of loading ROM data from the SD, from a USB interface or from an SD card. And it features an ARM microcontroller that simulates ROM and more, something like bank switching techniques and even more crazy stuff that we will go to at the end. This is what the cartridge looks like. So you can see at the back the SD card slot and the USB connector. And of course, when you want to go for hacking hardware, you need a console. For the console, I suggest, if you're going for PAL development, since we are in Europe here, you go for the Junior, because it's the easiest to modify with a composite output so that you don't have the need for a TV modulator. This is the whole hack. So that you just add 5 registers, a capacitor, and then you get the output. That's it. About €2 worth of materials, including the connectors. And this is what the console looks like you want to go for. So let's take a look at the inside. What the hardware looks like. We've got the 2600, a ROM module which will run your code. You've got input devices, joystick, pedal, driving controller, keypad, trackball are available, and of course the output, the television or the composite output. So inside the Atari we have the CPU, which is a 6507, the little brother of the 6502. You've got a one chipset, which is called the RIOT. It consists of input-output ports, a timer, and RAM. So it's all, the RAM isn't a dedicated chip, it's just inside that RIOT chip. And we've got the television interface adapter, which is for the output of the audio and video, and also does some of the input. So how are these connected? The ROM module and all the chips are connected via the CPU bus. The input devices go into the RIOT and also into the TIA. And of course, you get the output to the television device also from the TIA. So let's take a short look at the CPU. Since all you are here have already coded, we can cut this short. It was designed by Chuck Peddle. There's been a very in-depth talk by Michael Stile. And it's clocked at about 1.2 megahertz. So let's compare it to the 6502. It has a smaller chip package, so 12 pins are missing. What's missing? 3 of the address lines. So we only have an address space of 8K, which has been repeated 8 times. So the internal, you still have the 16-bit, but only 13-bit are external. Both interrupt lines are hardwired to +5. So no interrupts. And some not so very important pins have been removed, and also 3 unconnected ones. So let's look at the RAM, I/O, and timer, short RIOT. It's a very common companion chip for the 6502 family, especially in the beginning. It figures the 128 bytes of RAM. It's all the RAM that's really inside the console. You've got 2 I/O ports that are 8-bit wide. One is used for the 5 console switches. You have got 2 difficulty switches, a black and white switch, reset game, and select game. You've got 1 for the I/O ports of both joysticks. And these are only the directions. The fire buttons are connected to the TIA. And we have got a timer that it's capable of sending interrupts. but the 6507 is not capable of receiving interrupts. So let's take an overview of the memory map. As I stated, we've got mirrors of the memory map. Usually it's get divided in two parts. In the I/O timer RAM part, that is located in the lower half of this addressable space. And in the higher half, you've got the ROM module. Usually they are addressed either in one go through, or they are addressed in taking the first bank and the last bank. So the cartridge port has 24 connectors that are resembling the 24 pins of an 32K bit, also for kilobyte ROM or EEPROM. We've got 3 power lines, two ground and 1 +5. We've got 8 data lines, and we've got 13 address lines. So that's all. These are the 24 pins. Is there something missing? I think there is. First of all, there is no chip select line. During the definition of the 2600, it was defined that a high active A12, so that they can just use the address bus to the chip select to address the chip select. There were pins, there were modules that had an EEPROM and an inverter just to get that chip select. And the most missing part is the read-write line. So this is only a read. Well, we have there were 2 ground lines, and it's a bit of a shame that they didn't use one of these lines for read-write line. Would have made things such easier. So I don't go into the exact mapping what is make line. It is usually addressed in the RAM between address 80 to FF. The I/O and timer is usually addressed at 280 to 29F. And again, these are mirrors inside the address space, which can be pulled out of the exact mapping at the top. So we've got the I/O ports on the RIOT. They all have a data direction register, and of course the data register, so that you can switch them through output. I managed to link one of the control ports from the joystick to the other control port of the joystick on the same console and pipe data through there. So we've got the timer status register. So you can read the timer in 2 different modes with disabling the interrupt and enabling. I specifically chosen to select this address for reading the interrupt flag register. So even though the interrupt isn't triggering, the interrupt of the RIOT isn't triggering the interrupt on the CPU, we still can read if an interrupt has occurred, even though we are not triggered by it. And you can start the timer either without or with interrupt enabled in 4 different modes. So the times that are there are clock cycles of the CPU. So, yeah. So the RAM, this is the fun part. We've got 128 bytes of RAM. That's all there is, half a page. It's needed at 2 locations. In the documentation, there is the space called in the 0 page for the variable, so your states that you save. And you need it for the stack, so your jump to subroutine can store where to come from again, or you can go back again. And these are used as mirrors. So when you write to 1FF, you can read it from FF. So in the whole documentation, it is stated that the stack is also running from FF from the programmer's point of view. And this is my favorite quote. The microprocessor stack is normally located from FF on down, and the variables are located normally from 80 on up, hoping the 2 never meet. So let's take a look at the tier. This is the only chip that has been developed by Atari themselves. All the others were MOS Semiconductors chips, MOS which got bought during the design phase of the Atari by the Commodore company. So again, this is mirrored a lot of times. We've got space for 64 registers. There are 14 that can be read only, and they are mirrored inside that address space 4 times. And we've got 55 write-only registers. All the registers in the TIA are only one direction, either read or write. You cannot, once you've written something, read it back. So these are the read registers. Most of the registers are for detecting collisions between all the various objects that are available. And there are also some input registers because the RIOT chip is not capable of handling any analog input that was needed for the pedals. And also we needed the fire buttons. The fire buttons are 4 and 5 and 0 to 3 that are the 4 pedals that can be connected. The write registers are a lot more. They control the whole syncing, the graphics, and also you get to clear the collision registers. And a bit left there on blank is the audio part. These are just for reference. As we need them during the talk, they will get introduced. So let's take a look at the display. Again, most of you know how the television works. It was connected to, we go through the whole screen line by line, and the color gets set as the beam travels along. So we've got scan lines, 262 for NTSC, 312 for PAL. During this one line, we've got 228 color clock cycles, as they are called in the manual. And a color clock cycle is what would we understand as a pixel. But since we don't have any frame buffer or something like this, this term wouldn't really fit right. So how is the relation to the CPU? The CPU runs at exactly 1/3 at the speed of the TIA, because the TIA generates the clock for the CPU. So we've got 76 CPU cycles to get on one line, compared to the 36 of the C64 we just learned. So we've got, again, the vertical sync and vertical blank area. These are about 40 or 48 lines. These are, although they are written here as fixed values, these are just the parts, again, as the overscan part, that are just not seen because the television does not display the whole frame. Compared to the horizontal blank line, these are really hidden. There's nothing you can draw in there. This is just time that you can prepare to do something. So what we are left with is a drawable area of 160 color clock cycles and 192 lines or 228 lines, comparing as you are using NTSC or PAL. The lines are not fixed, as I said before. So, as I mentioned earlier, we've got no frame buffer because RAM was very expensive back then. I figured today a gigabyte of RAM is cheaper than what costs a kilobyte of RAM back then. To convert graphics, the graphics capabilities to a dumb frame buffer, you would need 30K of 7-bit words, so this isn't even addressable through the 8K address space of the 6507. So a completely different approach was taken. We program the video chip while the image is displayed. The advantage is the chip to produce was very cheap, and it's very flexible. The design phase was quite costly, though. The disadvantage is, since we are doing all stuff like this, the CPU is really occupied just on shuffling the data into the graphics controller. So this is called racing the beam. Instead of running frame by frame, you're drawing line by line, And you also change the register as the beam travels across the line. So you are really racing with the beam that displays the pixels. If nothing is changed, the next line is drawn like the one before. So very typical back in the days where SvOlli was, the games were designed on the hardware. If the software you wrote crashed, you would just see some stripes going down the whole screen. So the other side is we don't need any registers for Y components because we are doing it as the beam travels along. So we've got to count on which line we are. So, and yes, the big advantage compared to the C64 is our sprite is 6-bit wide, but it can be as high as a screen without any problem. And as I started the introduction, you just need to tell the tier what to paint while it's already painting, so raising the beam. Let's start with the most basic part. These are the playfield graphics. The playfield graphics are 4 color clock cycles along. So if you divide 160 through 4, you see there are 40 bits of information. So the registers responsible for the playfield generation are the color registers, color playfield, color background, and the playfield data. But how are we going to fit 40 bits of data into just 3 bytes? It's simple. We've got a control register in which we can tell if we only have 20 bits of data. And once these are drawn, we can decide if the same data should be drawn again for the second half or if it should be displayed in a mirrored way. We also have other bits there. We can use the player colors instead of the playfield color and the left half is then from the player 1 and the right half is from the player 2. It was implemented to show scoring. And we can also decide if this playfield should be over the sprites or the sprites should be over the playfield. So let's take a look at the playfield data registers in depth. So this is what is used. I've numbered the bits through so that you can see how they are displayed during the beam travels along. It looks like this, if they are mirrored. Once you write your own code trying to display something, you will get something wrong, most probably. I was cursing about 2 hours to get things done. In the repeated way, it's displayed in this bit order. And what you can also do is you can change it as the beam travels along so that you can display something else in the second half. This is essential for demo coding if you're going to use the playfield graphics, and I guess you will. Well, and the whole bit ordering isn't intuitive. So, sprites. We've got 5 sprites. Only 2 of them are what I would call full sprites because there can really be graphical data in there. They are 8-bit. The other 3 sprites are just can be only be turned on or off, and they've got 1 pixel in size. Why? Because the hardware was designed for running combat, or what was called tank in the arcade. So you've got your missiles, you've got the players. So these are the player sprites, the missile sprites. All would run to Pong, the video game. They were called Video Olympics on the 2600. So you got your players and the ball. So even the naming of the sprites come from these games. How are sprites placed on the scene? As I first read the documentation, I thought, oh, this isn't so hard. You've got your register, you write where you're going to get it, and that's it. Then I read, as I mentioned, let's not forget this one. Again, you enable it before the beam reaches the position. How do I enable the sprite? I write something else in there. I write in there something else besides 0, so the data gets displayed. The X is more complicated than I thought at the beginning. We've got reset registers where you can write into. So what does reset mean? It does not take any values I intended, or thought of at the beginning how it would be. And reset has a different interpretation there. It's not the left side of the screen, but the current position on where the beam is right now. So this leads us to the point where the TIA is 3 times as fast. So how are we going to get it into fine-tuning? Because we can only put it at every 3 color clocks. There are moving registers where you can say move by the amount of 8 to 7 pixels. And what was demotivating really hard was it's not like you get it from the mathematics. The negative is left and the positive is right. Now it's reverse order. So, but writing something in there doesn't really move the sprite. You've got another register that triggers at what you have prepared for the move. And as one of the very rare benefits, you can clear all the registers at once by writing at this register. Colors. This is really one of the beautiful parts of the 2600. We've got 128, and on the NTSC console, they look like this on the color palette. For PAL, we were already a bit handicapped because the chip has to be redesigned and some of the logic has to be reused. I have a question.
Yeah. Can you imagine a reason why they designed it this way, that these sprite position registers are so hard to write?
Do you have the answer or?
No.
Oh,
I'm really interested.
Here was one of the very talented 2600 coders here. He was raising his arm. And do you have the answer to the question? Yeah, okay, then do my work.
Hi, I'm Jack. I'm one of the probably 4 active VCS coders. And I also thought a lot about this question. In fact, the answer is quite simple if you think about the time that the CPU has to really write in a single line. So it's 76 cycles. And if you now think about load and store, which means 2 cycles for load and at least 3 for storing, you have 5 to write a single register. And if you now take the possibility to, in the same line, reposition 5 objects, it would simply eat up all the time you have in a line to do this. And therefore, first of all, they saved a lot of hardware. You have no X position stored in hardware where you need to put in and store it. So this is completely saved. And it's much faster to just say reset, and you have coarse positioning. And then you have this combination of preparing all the fine-tuning and then do it in one single line. So if you think about it, it's all about saving space and saving time, because the CPU would simply not be fast enough if you want to do it within multiple lines.
Thank you. So back to the colors. A bit of the logic was reused to generate the PAL color, because generating the PAL color is a bit more complex than the NTSC color. And so a bit of the color table was sacrificed for this one. But PAL was lucky. The guys who run CCAM, they are really screwed. So let's take a look. We've got 4 color registers. And these are shared between several objects. As I mentioned earlier, there is the playfield color that can be changed to the color of the players to indicate scoring. Usually the playfield color is shared with the ball sprite, and you've got the background. And of course, the missile also matches the color of the corresponding player. So the question, would you want to do a demo in NTSC or PAL? It divides into 2 questions, color and frequency. For color, the question is clear. NTSC is better, definitely. Also, the color table is better organized, and you've got more colors. For the frequency, I think the 50 Hertz is better than the 60 Hertz because you've got more raster time to do stuff on one frame. For gaming, on the other side, I think 60 Hertz is better because the games run more fluently. And I've also seen some code that uses the difficulty switches for adjusting color map and frequency, namely the game of Boulder Dash that was released last year. So how are we going to keep things in sync? Since we are writing since writing the registers is essential, especially the reset registers of the sprites, we really need to know where the beam is. On the line, there are 3 rules over the thumb that you're going to do things. On the line itself, you count the cycles, of course. Every opcode, for every opcode, the time it takes to execute is known. And you've got this one cool feature that the C64 doesn't have. You can write to one address line and the CPU stops until you're on the beginning of the next line. So timing to the correct exposition is really simple on this one. But this is, without this, programming this hardware would be nearly impossible. If you cannot predict on how long some code will take, you can start the timer and wait for it to time out after your work is done. For this one, I've brought a small code example. It's close to real life. This is what I had done at started coding. I've used up I had a delay. I used the timer for the divided by 8 clocks. I did my stuff, and then I read the timer to see if it already is 0, or I waited for it until it reaches 0. So I was sharing with some other guys at Atari Age, and one told me, what you do is correct, but what will happen to you if there's this one really rare course where it already is 0 before it reaches your wait loop? What then happens is the timer, once it reaches 0, starts in clock cycles, starts counting back from FF back to 0 so that you can indicate, or you can see how many clock cycles you have missed. For this loop, that's crucial, so I'm going to wait another 250 cycles, for example. So there's a better way to do this. You start, again, with the same, and this time we add 8 to the address, so we're going to do it with the interrupt. We are not capable of receiving interrupts, but we can, as I stated, the register, we can read the state, the interrupt state of the RIOT chip. So once the interrupt occurred, we are through. It has also occurred if we are getting into the wait loop too late. So we are just losing about 4 clock cycles, 5 clock cycles. And most times, if you're going to sing with a W-sync register and something like this, you will then catch up. So what we've learned here, even there's no interrupt line on the CPU, the interrupt of the timer is not useless. Audio. It has a very unique sound. You can, I think you can tell a 2600 by the sound already. We've got 2 voices, each divided in 3 registers. One is the volume. We've got the frequency. The bass, each tone has a bass frequency, and it gets divided by 1 to 32. This is chosen with this register. And we've got a control bit that decides on what tone generator is being used. So we've got 16 possible combinations. 11 of those are unique. Most of these settings are not really good for music. They were intended for effects like motor noise, shots, flying UFOs, stuff like that. So the sound generation can be looked up in 2 steps. the step one is to create the basic signal. For this one, the control register, define the pattern, and the base frequency. The base frequency is the color clock divided by 114. And there are also patterns that are reused inside the chip, but with a different clock, or with a different base frequency. And what's being done is that you've got a rectangular, or some rectangle that you get out there, and it's going to get shifted out bit by bit. So let's take a look at all the possible waveforms. So some of them really sound very odd. Stuff like this can't even be told as a note because it's so low. The really interesting ones for doing music are the 4 and 5 and the 12 and 13. They are pure rectangles. All others have some interference in there so that they're going to create a nice distortion sound. So let's take a look on how they are on the keyboard. This is the setting of 4 and of 12. And as you can see, for composing music, this is challenging. Not only that you are limited in the notes that you have, but also some of these notes are very far off, about something like several percent. And there is also this nice short story that for one game, the designer bought some cheap keyboard, handed it to a musician after he marked all the notes he's allowed to use on the keyboard. So here, this is what all you can use to create some music. Go for it. So after we've created this signal, this signal is multiplied with the volume register. And I forgot to mention it. There was one that was just high. That was just a one that got pushed out all the time. This is now getting useful. It's not only this is silence, but it's also by changing the volume, you can get some digital audio out of it. There's a really nice demo by Chopin where he's perfected this one together with Knöcki, I think. About 1.5 minutes of digital data pushed out through a 32K ROM. Very nice, very impressed. Also very impressive is a game, a modification of the original Berserk module, where they took the samples of the arcade game and put them in there, and they get really close to the original. It's really impressive. So, but you want to do music for your demo. For your demo, if I'm going to take a look, either you will want to write your own player, or someone who's really good with music has done it for you. He's called Paul Slocum, and the routines are called Music Kit 2. It's some kind of a tracker play routine, but no one has written an editor yet. The music is set up by creating tables, or by setting up tables with the assembler. You've got a nice include file where the music is inside, or it's described with, and with very detailed information on how you're going to get things done there. So it's very well documented, but there's just no editor. Again, source code and format. Now let's going to get on how to get things done. Let's talk about your first program. I was stupid at trying my first Atari code. I was going with the documentation, say, okay, I'm gonna do the V blank, and I'm gonna do, I've got to wait for this, and then I've got to switch things on. And after 2 hours, something like this, the screen was black still. I got fed up and said, okay, others have succeeded, let's use their code and start from there. It's really, there's a lot of code that works fine as a template. If you can't find anything, take a look at the links at the beginning. the quartile side is the best reference that there is in one place. And it's going very in deep. So for your code, you need your very own reset routine to clear the registers and the RAM. You need some code to display, to run the TIA. This is called the kernel. And of course, you will want to do some pre-calculation on the next code. Usually on the game, this would be the game logic. So if you've gotten your first non-black screen, I suggest you go for the asymmetrical playfield, as I introduced earlier. Let's take a look at it again. Short recap, the playfield looked like this, if you're going to do it. So once the beam travels along, and it has passed on displaying the first nibble of data, you can already rewrite it to display, or what to display the next time. Again, so but you got to take care of that you're going to do it in the right direction. So again, warning, bad code ahead. This was from the very first code I've really done on the asymmetrical playfield. So what I start here, I'm going not for the register names. I will. This is the PF0, PF1, PF2, and this is the W sync, so that you're going to get in sync with the beam. I've chosen just to show it by the addresses so that we can see it's really on the 0 page. All we're going to do is already in the 0 page. So what we're going to do is, first of all, we do some preparations. Because we'll come to later on what we're going to need it for. We're going to do 8 lines of each block we're going to display is going to be 8 lines high. Then we're going to wait for the start of the next line. Then read from our virtual frame buffer the data we're going to display, write it in there, then go through all 3 registers. And once we've done that, we are already, or we should be already at the place. I'm not really sure. I wanted to check this up, but didn't have the time. So that we can do it again with the next half. And once the beam travels along there, we're going to decide on what to do. First of all, we're going to do a jump back because we want to do 8 lines. After we're going to do 8 lines, I'm going to add to my frame buffer that is line-based oriented. I'm going to add 6 bytes so that I can get the next line of code. And once I've done 8 lines, 8 lines, no, 8 lines of data, I'm going to quit the whole routine because this is what my definition of the frame buffer was. So why is it bad code? I'm wasting a lot of clock cycles. In this place, if I'm going to go for not a line-based frame buffer, but a column-based frame buffer, I wouldn't have to do this addition. And if I'm going to do it upside down, I don't even have to do the compare. So I'm going to save. I'm going to need, again, for the decrement index register, 2 clock cycles, but I'm saving a whole of 6 clock cycles, which is about 8% of what I've had on the whole line. So this is bad code. So let's go back again for the sprites. Sprites, as I told earlier, can be 6 bits inside in width. So this is 1 byte. It was chosen this way because of the 8-bit architecture of the CPU. Again, it can be as high as you want to, and it works on the line-by-line basis. So the available 2 missile and ball sprites, they are not. They can be used to something cover stuff up and something like this, but they are not really a point of for us of interest in this point, as they can be only be turned on and off. So the interesting thing about the sprites is they are not only 8 bits, but they can be stretched or multiplied. So we're going to do, these are tried to be in scale. So we've got the option to double the size of a sprite or to quadruple it. And we can also do a repetition with 8-bit of a sprite, 8-bit space, a gap in there, and then again 8-bit of again the same sprite. Mirroring of the sprites is also possible. There's a bit where you can say that the data should be displayed in a reverse order. And the missile and ball sprites can be also of different widths with up to 8 clock cycles, but only in power of 2 steps. There's one thing in this whole combination of things to do with the sprites that is really interesting. This is this one. Because we've got 3 sprites. Each can be 8 pixels wide and can be repeated 3 times with an 8-pixel gap. So we have got a gap that is exactly the same size as the size of the sprite. What we're going to do is we're going to interlace them, display them one after another. And now all we have to do, simple, as the beam travels along, change the sprite data as it's going to be displayed. And what we've got there is one 48-pixel sprite that's going to be the most valuable thing you've got in there to get things on screen. But for the exact timing, we're going to need a helper. The helper is called vertical delay. It enables something like a one-step pipeline inside the TIA graphics chip. It was originally intended to save time during the display of a game scene. So in the original days, it was very common to have what they called a 2-line kernel, because the graphics only changed every other line. Not every line that's going to change, but every other line. And the vertical delay was implemented so that you can, by writing in just one of the player registers, you can change both. So what's done there back then? You're going to set the vertical delay for player 0, write your data in there. The data isn't changed still yet. It is just in the pipeline. And once you write in the delay and the playfield data and the sprite data of the player 1, then the other data also gets pushed out of the pipeline to the display. We use this one not to do it on every line, but on every not on the line, but as the beam travels along. This also works. Okay, this was telling already. So let's take a look at the code. Let's go for the full thing. First of all, this was just some increment, so I can waste 6 clock cycles in just one line of code. So this page is already full. We're going to load from a 0-page register on what is left of the data to display. We're going to read from a 0-page index the data, write it into the first one, then in the player 1, write it into copy the next one into player 1. Now the data gets updated for player 0. After that, we also write the next one in there. Player 1 gets changed, but player 0 doesn't get changed because we're on the vertical delay. So now we've got 1 in the pipeline and also 2 on display. So and this is what we need on preparation. Now we're going to do some really some stuff so that we can get at all the data we need for the next pushes through these pipelines already in handy. So we're going to need all the registers that are available. So once we're going to write the next data for player 1, this gets then pushed to the display and so on and so forth. And the left one, what I'm going to do what I've already done, because I need to push the last byte out of the pipeline. So this is on how it's done. And I was really getting also in analyzing on how this works. I missed the vertical delay part and was really couldn't understand what was happening. So this is really the one good clue that we're going to get out of here, probably. So we still have to do some cycle exact positioning. It's not as easy as on the Commodore 64, where can you do some interrupts in a line and then you're going to get it. For the exact positioning, we're going to have to divide our X position into two parts. The one part is the CPU clock and the offset. So we're going to know the CPU clock is divided by, is the color clock divided by 3. So we're going to do the remainder. I've been wrecking my brain on trying to get something done there, and I came up with a simple solution. I used a table, a pre-calculation. On the lower part, I've got my divisor and my divider, and on the higher nibbles, higher bits, I've got my remainder. Because I can move this one to the part at the registers where it's needed for the move register. They are not counted started as the bit 0, but on the bit 4. And also important is we also need, when we push it in there, add by 1. Because as we're going to do our reset, the STA, or the write to the 0 page takes 3 clock cycles. 3 clock cycles times the 3 times faster of the faster being of the video register, we're going to move 9 pixels along. So we're going to get this 1 pixel we've got too much back again. So this is plus, as I introduced earlier, it's going to be more to the left side. So again, for really doing the calculated for wasting the exact number of cycles, I came up with some pretty clever code that I extended a bit more, which I called the Clockslide, because it's really, we're going to jump in there and, on a slide. What we're going to do is kind of calculate about this address plus X. This is what's going to be read from the division by 3 table, what we need. And we're going to push it -1, so that the label is 1 off. Because when the RTS is executed, it's going to jump 1 bit further. So what does the clock slide by like? In the assembler source code, it looks like this. So let's go it the other way around and take a look at what the CPU sees. If we're going to do an even call, let's go it from the top, from the bottom up. We're going to get there from EE. We're going to waste about the CMP.EA, $EA, 3 clock cycles. If we're going to get 2 bytes earlier, we're going to get 5 clock cycles. 2 bytes earlier, 7 clock cycles. So you get the pattern. So what's going to happen if we're going to jump on the odd calls? We're going to find there a knob. So again, we're going to then compare, it also adds up by 2. So we're really going to get, just by jumping, wasting the exact number of clock cycles in a range. It's not really up to 0 or down to 0, but to 2 plus the RTS plus the preparation. But we have the very fine control on what we're going to get, or what we're going to need for placing the sprite on the right position. You can also do 96 pixels. This is, but with a trade-off, because you can do interlacing. Probably you will go from the close to the far stuff, so that you can not only interlace the sprites during the display, but also on when you switch the position every other line. On CRT-based monitors, this looks really beautiful. You probably won't even notice that there is some interlacing there, but it won't work with TFT monitors. Stellar has, for this one, called a phosphor mode that can be activated with Alt-P to simulate a CRT-based monitor. Again, if you're going to want to do 96 pixels, so you're going to get either flickering or you can go for gap lines. These are typically black lines in between the pixels. So let's, at the end, let's go a bit talking about the barriers. We got the barrier because of only 4K modules. As I mentioned earlier, we've got Tjoppen who did 32K module. How it's going to be there? As an example, I'm going to use the 91 invention of the 8-ROM module and how we're going to fit 8K in a 4K address space. We're going to use bank switching. So we've got our address space with 4K, and there we've got 2 banks. And how we're going to get from one bank to another by reading some honeypot address. So once we've got this, we're going to switch there. Once we're reading on bank 0 this address, we're going to switch over to bank 1. But what we're going to do there is something like the code starts here and ends there. So you're going to really be byte exact on what you're going to code. And this is this byte exact coding is easier done with the DESM assembler than with the S65. So the cartridge type was called F8 because of the honeypot address. We can also get more RAM. But as I mentioned earlier, we have got no read-write line address. So how are we going to get RAM reading and writing? Solution is to use different addresses. We've got a write port that starts at 1000, and a read port that starts at 180. So if you're going to store something in 1000, we're going to read it back at 1080. And the variation of this is called, usually it's ended with SC for super chip, as the additional RAM was called originally. There also is a very extended cartridge that's called the DPC cartridge. And this is called, on the demo scene, really it is cheating because you're going to use the computing power of the ARM microcontroller on the Harmony chip to assist you on your 6507. It is based upon the DPC cartridge that was used for Pitfall 2. It's a great game, and when you're going to see it, it really doesn't look like a VCS game at all. So the technique was invented there, it was patented, and some folks at Atari Age took this one and developed it further using the microcontroller and get some cool stuff in there. The base part of it is that you've got 6 4K banks of ROM. You've got 3-channel sound using one of the TIA sound channels. This is done by every line reading the sound register address of the module and copying this one over to one of the TIA sound channels. So you still got the other TIA sound channel for sound effects. And you also got additional ROM available that's not addressable directly, but through data streams. And this is what I'm going to look at last. What you've got there, you enable it through some honeyspot again. You're going to use your sprite. And what this fast fetch enabling does is you're going to get a mode where the LDA we're going to do there gets patched. It gets patched in the way that the byte that declarates the data stream you want to read, it changes the 8 to the actual ROM data we're going to use for our graphics data. The same for the second data stream. And what we're going to do is write it back there in the sprite writer. So usually when we're going to read it from ROM, we need about 5 clock cycles for the read and 3 for the write. This way, we only need 2 for the read and 3 for the write. So we're saving 3 out of 8 clock cycles. And of course, if someone want to do the hard way, he called someone who takes this shortcut a cheater. It's understandable. So, I still owe from the last talk an explanation on how it's done. I chose of one of the examples of the very late development. I really find impressive on how this planet is drawn, because it is much wider than anything that I've known from the sprites. This one. And so we're going to just show you on how to use Stellar, on how to determine how this one is done, just after any left questions. No, not done.
Hello. Yeah, does the kind of 2600 development scene kind of mostly use emulators, or is there scope for making a cartridge-based game that does use these kind of tricks?
Last year, there has been some huge release in terms of the scale it was. After on and off development of about 10 years, there have been a release of Boulder Dash, originally done for the C64, and it's been ported to the 2600 using a very special cartridge with an official license from First Star Software in a limited edition of 250 copies. There are still new modules made every year, new games made every year, and they get sold.
Okay. Yeah, because I was thinking that you could generate the ROM, I guess the CPU instruction stream with an FPGA or something like that, and have some really awesome effects where basically changing every pixel as quickly as possible.
Yeah, you could do something like this. The DPC Plus cartridge goes already in this direction.
Yeah.
As I've read, there's also the ability that you can call something inside the ARM processor and get results from there and use it in your 6507 area.
Yeah.
There are ways like that, but we are up here for the challenge, aren't we?
Yeah. Yeah.
Hello, I'm Mike of Cubics. So another method to draw the playfield could be to unroll the whole loop and then draw it from LDA, and this would give you much more time to change things. Is this also a method that is normally used?
Yes.
Okay.
just one. Yes, I already did it.
Yeah.
For loop unrolling in a very time-critical space where I used some restart bars and stuff like that. I can show you afterwards.
Okay, thank you.
So,
just one comment regarding what I tried to explain regarding why is this strange thing with the sync and the H-move registers. It is not very useful when you just think about positioning the sprite once. Yeah, it looks weird, yeah, and you don't say what you see, what you save. Well, what I was referring to, if you maybe later on, if there is time or after the show, you can show game like Jungle Hunt or Jedi Arena, where you will see lines moving up and down, or you have something like a liana going left to right, or something like a sword that is moving. And if you want to do that with a CPU, it would mean that you have to add or subtract in every line. And here you can just do something like relative movement and click a button, and the hardware moves this sprite, and it can even move 5 sprites at the same time to any direction with a relative movement. And this you could not do with real computation in that line.
So, just as what I wanted to show you, wanted to look at is Solaris, the game. It's a very fun game to play. It's very hard, and but what we're going to want to look at is on how these in position, how the planet is drawn. So what we're going to do first is just go through the scan lines. I need a bit of a trigger finger here. Where we're going to see. So now we're going to switch to another panel where we can see at the hardware itself. And now as we're going to go through that part line by line, we're going to see that the data adds up. As what we also see is that it gets delayed by 1, so writing to the other color register really triggers the change there. So what we're going to see is how the sprite data moves up, is changed. Right now, as we can see, there's no movement there. And as we're going to take a look now, the sprite data from the first line of the planet itself, not from the ring, is loaded. And as this one gets written again, the change from the last time gets written to the player field data. And what we are going to notice is this time is double size. So we've got twice the width. And this was something where I couldn't get my mind on first. What we're going to do, what the coder here does, is that the sprite is double in size, but the movement isn't. So you're going to get some, as you go line by line, you get it very smooth there. So, but the real interesting part about this one is we've got here some really wide space and how this one gets handled. So we're going to see there right now that the graphics data is empty. We also see something like this. The ball sprite gets enabled. Why? We're going to see in the next line. It has drawn a star. One should be here, something like this. And what we're going to notice now is the player data is 0, so it's not going to be displayed anymore. What's happened? The missile sprite has taken over. The missile sprite one in size, and it's going to get moved now to the right. Step by step, you can see as, how it gets moved any further. And then we're going to get back our player sprite. And so we're going to use the missile sprite and the player sprite to get the illusion of a very bigger sprite than we already have. So much of the things you're going to accomplish is by tricking the viewer into assuming something that isn't. And this is the real fun part about coding on the VCS. And I'm also very proud that I coded one idea for a demo and showing it to one of the best coders I know. And just by looking at what's happening on the screen, he couldn't tell on how I was doing it. And that's what I'm proud of. So, but we can also, if we're going to take a look back, this was the hardware we're going to learn. There also is an easy way. You can switch through another visual mode in the emulator and see now, where's that? So we're going to see on the screen that now the color of all items are not read from the color registers, but hard-coded to the type of the sprite we're going to use. So we're going to see, okay, one player sprite is used for the ball, another player sprite is used for the ring, but here we've got the bright part. This is the missile sprite because the corresponding missile sprite is drawn a bit lighter than the player sprite. We've got our playfield data back there, and we also can see that the spaceship of the game is also using a sprite with different sizes, the missile sprite with different sizes to trick us into thinking that this sprite is wider than it already, or that it is actually, yeah. So there are a lot of things to learn from these games just by really looking at on how in this mode. And the white part here is the what can be compared to the bad lines of the C64. It's when you move a sprite, you're going to get a bit of where you can't display any data. So this was that. And for next year, I want to see more than one guy doing demos. Thank you.